Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the Salane pole synchronous motor, and we understood that there are two synchronous reactances, one along the direct axis and the other along the quadrature axis. Now, let us try to draw the phasor diagram for a Salane pole synchronous motor. So, here what we have here is that we have two synchronous reactances. This is our d axis or the direct axis. So, the synchronous reactance is x s d, and this one is the quadrature axis q axis or the quadrature axis, and the synchronous reactance here is x s q. So, we have to draw the phasor diagram for a Salane pole synchronous motor. Now, we have a field excitation in this case, and the field excitation produces a flux in the direct axis. So, this is the direction of the field flux phi f, and we have the stator. The stator is also a cylindrical stator. So, this is surrounding the rotor. So, we have a cylindrical stator like this, and the windings are placed in the stator, and when it rotates, when the field rotates, field is rotating at certain speed. So, when the field rotates, this induces EMF in the stator conductors. So, that induced EMF is E. So, we can draw the phasor diagram as follows. We start with the d axis, that is the axis of the field pole. So, we show it by means of a pole structure. So, this is the d axis, and the q axis is right angle to the d axis. This is the q axis. Now, we define we have a current which is I s, the stator current, and the current and MMFs are in the same direction. MMF is nothing but current into the number of turns. Now, when we have this current I s can be resolved into two components, one along the d axis, other along the q axis. So, I s along the d axis, we can project this along the d axis. This is called I s d, the direct axis stator current, and the current along the q axis is called the quadrature axis stator current, that is I s q. Now, the field current is along the d axis, that we have already seen, that we have the field current I f, and because of the field current we have an induced EMF, and the induced EMF is E, that is the induced EMF, which is the normal induced EMF that we saw even for a cylindrical rotor. Now, this induced EMF is E, and to E we have to add two drops, one drop for the d axis reactance and one drop for the quadrature axis reactance. So, we have different reactants for the d axis and q axis. So, first of all we will add the d axis reactance. The d axis reactance here is, this is the d axis reactance, and this is J I s d into x s d. This is our q axis. So, the reactance drop is right angle to the current. The current I s d is along this direction, this is I s d. So, the reactance is right angle to the current, the reactance drop. So, we have a J term here. Now, we will also add to this the reactance drop in the q axis. So, the reactance drop in the q axis is here, this is J I s q into x s q. So, ISQ is here, this is the reactance in the q axis, the current in the q axis. So, the reactance drop is right angle to that, and the total voltage, if we join these two phasors, we get the total voltage. So, the voltage V is given by this, which is a vector sum of E j I S d x s d plus j I s q x s q. So, we can write here. So, what is the total voltage V? V is equal to the induced EMF E, E is also a phasor, plus j I s d x s d plus j I s q x s q. Since we have two different reactances, we have to multiply the reactance with the corresponding current x s d with I s d, x s q with I s q, and that will give us the total voltage, that is V. So, this is the torque angle, the angle between the induced EMF and the terminal voltage V is the torque angle, and the angle between V and the current is the power factor angle. So, this angle is the power factor angle. So, this is our phasor diagram. So, we can find out as before what is the input power. P input is 3 into V I s cos theta. Since we have ignored the losses, that is equal to P out, the output power, that is equal to the mechanical power also. So, we need to find out what is I s cos theta. Now, I s cos theta is the projection of I s along V. So, I s cos theta can be written in terms of the current components, that is equal to I s q into cos delta, I s q is here. So, that into cos delta plus I s d. So, I s d is this current, and this angle which I s d makes with V is 90 degree, this angle is 90 degree, angle between the d axis and the q axis is 90 degree. So, 90 degree plus delta cos 90 degree plus delta. So, if we simplify this, what we get here, I s q into cos delta minus I s d into sin delta. Now, we need to find out what is I s d, we need to find out the value of I s q. So, from this phasor diagram, we see that I s d is appearing at this point here. So, if we find out the component of the voltage along the q axis and subtract it and subtract E from V, we get the I s d x s d drop. So, we can say that I s d x s d is equal to V cos delta minus E. So, what is I s d? I s d is equal to V cos delta minus E divided by x s d. So, this is our, let us say our equation 1 here. Now, we have equation 2 which has got I s d. Similarly, I s q is appearing at this phasor. So, this is our I s q x x q drop. So, if we take the projection of V along this axis, that will be V into sin delta. So, we can say that I s q x s q is equal to V sin delta. So, what is I s q? I s q is equal to V sin delta by x s q. So, this is our equation number 3. So, we have equation 1, equation 2 and equation 3. So, the value of I s d and I s q from equation 2 and 3 can be substituted in equation 1. Substituting the values of ISD and ISQ from equation 2 and 3 in equation 1, what we get is the following. So, what is IS cos theta? IS cos theta is ISQ. ISQ is V sin delta by XSQ. So, we get here V sin delta by XSQ into cos delta, and then minus ISD sin delta. ISD is given by this equation. So, minus V cos delta minus E by XSD into sin delta. Now, we have the product of sin delta and cos delta. So, we know that sin delta into cos delta is sin 2 delta by 2. So, we can further simplify this, that is equal to V by XSQ into sin 2 delta by 2. Here we will have minus V by XSD into sin 2 delta by 2 minus E by XSD into sin delta. So, this is the value of IS into cos theta. So, when we know the value of IS cos theta, we can find out what is the power. So, the power equation is P is equal to, or P m, the power output is 3 V into IS cos theta. So, IS cos theta we have evaluated in terms of the voltage, the reactance and delta. So, if we substitute this and simplify, we get the following expression, that is equal to 3 into V e sin delta by XSD plus V square into XSD minus XSQ divided by 2 XSD into XSQ into sin 2 delta. So, this we have obtained from the previous equation. Let us call this equation as equation 4. So, from equation 4 we, after we multiply here with V and simplify, we get the following equation. So, this is the power output for a salient pole synchronous motor. So, if we know the power, we can find out the torque. Torque is power by the speed. So, the speed here is the same as synchronous speed. So, we can find out the torque here. So, torque is power by the speed, and what is the speed here? P m by omega m s. So, that is equal to 3 by omega m s into V e sin delta by x s d plus V square into x s d minus x s q divided by 2 x s d x s q into sin of 2 delta. Now, in a salient pole synchronous machine, we see that T is a function of delta, sin delta, also sin 2 delta. So, because of saliency, x d x s d is not equal to x x q. That is why we have the term which is coming, that is sin 2 delta. So, here this is the normal synchronous machine torque. this is due to the field winding, synchronous motor or field torque, and the second term is called the reluctance torque. This term is called the reluctance torque. Now, x s d is not equal to x s q. Because of that, there is a difference x s d minus x s q. In fact, for a wound field synchronous machine, x s d is greater than x s q. So, because of that, the reluctance torque is positive for a silent pole synchronous machine. Now, we have also a class of synchronous motor called synchronous reluctance motor. When the field winding is removed and we have a silent pole synchronous motor, we call that to be a synchronous reluctance motor. In synchronous reluctance motor, the excitation EMF equal to 0. Let us discuss about synchronous reluctance motor. So, here the field winding is non-existent and hence IF equal to 0 and hence E equal to 0. So, the induced EMF equal to 0 here. So, we have this equation, let us say this is equation 5. Now, substituting E equal to 0 here, the first term vanishes, we only have the second term. So, the torque in a synchronous reluctance machine T is equal to 3 V square by omega ms into x s d minus x x q by 2 x s d x s q into sine of 2 delta. So, the torque does not depend upon the field, because the field has been removed, field current equal to 0. So, torque is a function of the applied voltage, the stator applied voltage, that is V square, and it is a function of sine 2 delta. It varies as sine 2 delta. So, it is sometimes quite attractive that the field winding is removed, but still the machine is developing a torque. So, but the disadvantage of a synchronous reluctance motor is that the field flux is 0, the armature will have to produce the flux and hence the power factor is poor. Although the motor develops a torque, it rotates at a very low lagging power factor. So, the disadvantage of this motor is poor power factor, as the flux is also produced by the stator current, So, we have discussed about the basic equations of synchronous motor, the cylindrical motor synchronous machine, also the silent pole synchronous machine. Now, these are fed from fixed frequency, fixed voltage supply. Now, what happens if we go for a variable voltage, variable frequency supply? We need to vary the speed. So, to vary the speed, we have to change the synchronous speed. So, to change the synchronous speed, we have to change the supply frequency. Let us discuss about variable frequency or variable speed synchronous motor drive. So, we have two types of variable speed synchronous motor drive. One is called a true synchronous mode, true synchronous mode and other is called a self controlled mode. So, we understand that to have variable speed for a synchronous machine, we have only one option, that we have to vary the frequency. Now, if the frequency is varied independently, we call those drives operating in true synchronous mode. So, frequency is controlled by or controlled independently. Now, when the frequency is controlled as a function of the rotor speed, that is called a self control mode. The stator frequency means the stator frequency is controlled independently. The stator frequency is controlled by the rotor position feedback. So, usually true synchronous mode drives are open loop drives, they do not have any rotor position feedback. So, we can call these drives as open loop drives and these are closed loop drives. The self controlled mode are basically closed loop drives. So, let us discuss a scheme for true synchronous mode, that is the open loop drive of synchronous motor. True synchronous mode. Now, in this case we go for what is called a V by F or V by F control drive. In the open loop. So, let us draw the block diagram. Here we have the reference frequency, the frequency is changed independently. So, we have a reference frequency here and which is fed to a delay block. So, here we have a delay circuit. And then we have a VSI, a voltage source inverter. And we have the synchronous motors which are fed multiple synchronous motors. So, let us say we have SM1 and SM2 and SM3. The stator is fed from the VSI, it is a 3-phase system. So, each one is a 3-phase system here. And the DC link is fed from a controlled rectifier. So, we have a DC link here, we have a DC link filter to filter out the ripples and the input is a 3-phase AC. So, we rectify the AC to DC and then we use the inverter. So, what we do here is that the frequency which is the output of the delay circuit is fed to the VSI directly. So, here is the frequency and then as before we have a V by f function generator, which generates this function. This is our frequency here, and the output of this gives the reference voltage. V star is the reference voltage, and then we have the triggering circuit. And the triggering circuit gives the angle alpha for controlling the DC link voltage of the VSI. So, here the frequency of the inverter output is f, and as we go on changing the frequency, the voltage is also changed. So, that the V by f is approximately maintained constant for higher frequency. At low speed, we have to add a resistance drop, just like an induction motor drive. Now, this is a drive under two synchronous mode, in which when we change the reference frequency, which is this, the actual frequency is changed after a delay, and the voltage is also changed to maintain V by f almost constant. So, we stop here for today's lecture. We will continue our discussion about the synchronous motor drive in the next lecture.